Okay, welcome to Robotics 1. In today's class, I'm going to talk about homogeneous transformation and solving forward kinematics problems. Let me start with the very basic approach. Step 1, whenever you see a robot or a problem, first see whether it has prismatic joints. So prismatic joints, or it has hinges or rotary or revolute joints. So first you need to check if it has prismatic joints or revolute joints. That is the first thing to do. Then second step, whenever you see the problem, is something similar to drawing the free body diagram. Come up with a kinematic diagram. So express that robot in a very simple graphical way. Third step, once kinematic diagram is done, is assign coordinate system. Assign coordinate system. Now, when you assign a coordinate system, remember the 4 rules that we talked about. The first rule is Zn has to passes through joint N. So Z axis has to pass through the joint. The second thing is your Xn has to be perpendicular to Zn and Zn minus 1. Now this rule is not applicable for X0, but if you have axis to be drawn for the frame 1, frame 2, you will have to make sure that Xn is perpendicular to Zn and Zn minus 1. You also want to make sure that Xn intersects Zn and Zn minus 1. In other words, Xn is not parallel. It needs to be intersecting. It needs to cut. And if there are cases when Xn is parallel, we'll talk about it. And the coordinate system is the right hand coordinate system. Then next step, can you please mute yourself if somehow you got unmuted, because it gives echo here. So, okay, thank you. So assign coordinate system, then find rotation matrix. And this is a super important step. And I just want to tell you that, remember, I derived 3 different rotation matrices, but I want you, for the time being, to remember only one rotation matrix. And I mean that. So this is the rotation matrix I want you to remember. If you recollect, this is the rotation matrix about Z. Now, this is the beauty of the coordinate system convention. Since we are going to use Z passing through the joint, the only rotation matrix that we will use is going to be the rotation matrix around Z. Then in the rotation matrix, next thing is find projections. The next stuff is find projections. Next step is find distance between frames. So between frames. And these distances should be the projections, or these distances should be in the coordinate system that is older. So in previous, and I will explain this to you what it means. Coordinate. And then set up homogeneous transformation. So homogeneous transformation is a 4 by 4 matrix, wherein first 3 by 3 matrix, this is the first 3 by 3 matrix. This is 3 rows, 1 column. This is 1 by 1, and this is 1 row, 3 columns, wherein here you are gonna have the projected rotational matrix. So this is super important. Projected rotational matrix. This is the distance in previous coordinate. This will always be 0, and this will always be 1. So we are going to start with, say, frame 0. So think about it. We have a frame 0. From frame 0, we go to frame 1. From frame 1, we go to frame 2. So we are going to have 0H1. We will have 1H2. And if I want to find out the overall homogeneous transformation going from frame 0 to frame 2, that will be the multiplication of these two homogeneous transformation. So this one cancels, and you land up with 0H2. So this is the overall process to find homogeneous transformation. And let me work out some examples. So I'm gonna go very, very slow in first few examples. And once we work out examples, 3, 4, 5 examples, this would come to you very naturally. But this is very simple and very intuitive. So let me start with problem 1. So in this problem, consider that I have a robot that has 2 revolute joints. So simple case, a simple robot. So this is the first revolute joint, and then this is connected to the second revolute joint, and this second revolute joint is connected to an end effector. So this is my revolute joint 1, this is my revolute joint 2. So since there are 2 revolute joints, this is called as RR robot. And some of you may ask me that this looks so simple, but believe it or not, if you have a robot, which is something like this, and if you have another robot, this is the planar diagram. If I were to draw the kinematic representation, so this is the first revolute joint, this is the second revolute joint. So the kinematic diagram is, it will be shown on the left. So before I proceed further, everybody understood that you have the link robot shown on the right, and on the left hand side, I'm showing a kinematic representation. Now this robot has some dimensions. So I'm gonna start with, I'm gonna call this distance as A1. This distance I'm gonna call A2, and my end effector is over here. This distance I'm gonna call A3. And please note, A1, A2, and A3 are all fixed. So what is the next step here? We have identified the revolute joint. We have drawn the kinematic diagram. Now let's set up the Z's. So this is my frame 0. This is my frame 1. And this is my frame 2. So my Z0 axis is here. My Z1 axis is here. And Z2 doesn't really matter, but I'm gonna draw Z2 something like this. Everyone clear about the Z's? Why did I choose Z's like that? Because the Z axis must be around the joint of rotation or joint of extension or the axis of extension. Now then I need to draw X0. Typically, X has to be perpendicular to the current and the previous frame. But since there is no previous frame before 0, I'm just drawing X0 the way I have shown. Everyone clear with that? Now, the next thing is I need to draw X1. What is the condition for X1? X1 has to be perpendicular to Z1 and X1 has to be perpendicular to Z0 and X1 has to be intersecting Z1 and Z0. Everybody understood this? So if I want to draw the X1, I will give you two choices. Tell me which choice makes sense. I can draw maybe X1 something like this. So this X1 is perpendicular to Z1 and this X1, if you were to extend this, is perpendicular to Z0. So the condition is satisfied. Now X1 is intersecting Z1 and X1 is intersecting Z0. And when I say intersecting, imagine that I extend this Z0 all the way up. So X1, we are good with. Now I need to do the same thing for X2. So X2 has to be perpendicular to Z2. X2 has to be perpendicular to Z2 and X2 has to be perpendicular to Z1. Is that happening? Yes. In this case, my X's are intersecting the current frame and the previous frame. Now, next thing is I need to set up the coordinate system. So don't worry, curl your fingers, right hand thumb rule, curl your fingers. X is your thumb, Z is your middle finger, and Y is your pointer. So X, Z, and do you agree with me that my Y is going to be like this inside the page? My Y1 is going to be like this, and my Y2 is going to be like this. So before I begin, I just want to make sure that everyone understood the coordinate frames. I'm looking at the chat window. If you have not understood, this is the time to ask because this stuff is super duper important. Yes. Yes, that is the kinematic configuration of the planar robot that I have shown. Yeah, yes. Oh. Yeah, of course, of course. You have a very vivid imagination. So think about the planar robot. We are not there yet. Hold your horses. So yes, Y-axis is going into the screen. Curl your fingers. X, Y, and Z. Your pointer is going in. I wish you could see me, but I'm showing everyone curling my fingers to the students who are present here. I'm looking at the chat window. Any other question? You guys have to get this right. If you don't get your coordinate frames right, you will never get a forward kinematics problem worked out correctly. So coordinate system is super important. Okay, the next thing, I'm gonna indicate the rotations. The rotation, this is my first rotation, theta1. And again, this rotation is positive. Why do I say the rotation is positive? Curl your fingers around the rotation and your thumb is pointing towards z-axis. That's why the rotation is positive. Again, there is one more rotation, which is here. Everybody with me so far? Someone online wants to know, can camera of your hand for the right hand rule? Oh, wow. Okay. I am going to start my video. Okay. Can you see my video?
No.
Oh, all right.
Yes, we can see it.
I can't see it.
He's still sharing his screen, so you have to select his camera.
So this is how it's gonna look like.
I can't see it.
If you see people's names and them speaking, you have to scroll through until you see Professor.
Oh, okay. Let me try.
Okay. Now you see me and you see everything. Okay. So curl your fingers. This is going to be your X. This is going to be your Y. This is going to be your Z. So if you look at X, Y, and Z, are you with me? Can you see me now?
Yeah.
Yes.
Okay. Everyone comfortable with the coordinate system? Oh, everyone comfortable with the coordinate system? X, Y, Z. Okay. Once that is done, what I need to do is I need to go back and I need to set up the rotation matrices. And this step is super important. So be very careful. The first rotation matrix is 0R1. This is the first rotation matrix. This rotation matrix is between the frame 0 and frame 1. Frame 0 and frame 1. So this rotation matrix is the rotation matrix cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. And why is the rotation matrix like that? The reason for that is the rotation is about Z. Everybody understood this? So this is the rotation matrix about Z. However, I want you to understand the next super duper important step. I want you to draw the projection matrix here. This projection matrix is, so you have x1, y1, z1, x0, y0, z0. So you have a rotation matrix and you have a projection matrix. And let's go through the drill. X1 is aligned with what? X0, Y0, Z0. X1 is aligned with X0. So this becomes 1, 0, 0. Y1 is aligned with, is it aligned with X0? No. Is it aligned with Y0? Yes. It's aligned with Z0? No. Z1 is aligned with 0, 0, 1. So which means my overall rotation matrix is the product of these two. And last time I showed you how to take the matrix multiplication, first row, first column, first row, second column, first row, third column, and so on. But hey, check this out. This is a unity matrix. This is an identity matrix. So any matrix multiplied by the identity matrix is the matrix itself. So this becomes cosine theta 1, sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Are you with me so far?
I have a question.
Yes. Shoot.
In the yellow parentheses, the first sine theta, should it be negative or is it positive now?
Sine, okay. Remember this matrix that I showed you earlier?
Yes.
Can you see the sine theta is negative?
Yes.
So that is the same matrix I'm repeating here. Oh, yes. And this is going to be negative.
Yeah, that's what I meant. Thank you.
Now, I need to set up the homogeneous transformation matrix. That goes by big H. And in this big H, first you will have cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. The last row is going to be 0, 0, 0, 1. Now the question is, what happens to these distances? Now let me repeat what I said. This is the distance between frame 0 and frame 1. So this is my frame 0. This is my frame 1. So I need to find out the distance between frame 0 and frame 1. And these distances should be expressed in the previous coordinate system. So you have two frames. You have 0th frame and you have frame 1. So the distance between the frame 0 and frame 1 should be expressed in x0, y0, and z0. Just a second. Just to let you know that the message you sent me privately will be shown to everyone. So if you have a private message, please text me on my cell. Don't send it to me and chat, because your private messages are visible to everyone. Okay. So what's your question? My question is, why is that identity matrix? That is how the identity matrix is defined. The what? I mean, like, do you mean that point is identity, like you treat that point as identity matrix over there? So if you have a matrix wherein the diagonal elements are 1. No. Is the origin 1, 1, 1? That's what you're telling. Is like the what? Or there is no origin. Origin is 0. Origin is 0, 0, 0. This is 0, 0, 0. I don't know why you use the identity matrix. Because that is the projection of x1 onto x0, y1 onto y0, z1 onto z0. That's why it is projection. Okay. Now the next super important part is the distance. And I want you to follow this carefully, very, very carefully. As theta is going to change, as theta 1 is going to change, do you agree with me? As theta is going to change, do you agree with me that the x and y distance between the frames will be changing, but the z distance is not going to change? So, and I will write this down. This is the z distance, this is the y distance, and this is the x distance expressed in x0, y0, and z0. So stay with me for a second. Can you see the distance between the z frame? So I'm gonna show this just so everyone is comfortable. Let me show it to you like this. Kinematically, it doesn't matter, but from visualization, some students may find this better. Can you see that the vertical distance is A1, and that distance does not change. And that distance, and I'm gonna show you the arrow. So be very careful with this. This is how that distance is. So it's a positive A1. And this distance does not change no matter what happens to theta. Whether theta 1 is 0 or theta 1 is 180, the distance, z distance between the frame 0 and frame 1 along z naught is not going to change. Any questions here? Now let's look at x and y. When theta 1 is 0, when theta 1 is 0, the x distance is going to be a2 and y distance is going to be 0. Let me repeat. When theta 1 is 0, x distance is going to be a2 and y distance is going to be 0. But theta 1 is a joint parameter that could change. So now my question is, for an arbitrary value of theta 1, say if the value of theta 1 is 30 degrees, 40 degrees, 50 degrees, what is the distance between frame 0 and frame 1 along x naught? And I'm going to write this here, and I'm sure that you will see it in just a second. It's going to be a2 cosine theta 1 and a2 sine theta 1. So please note, these distances are going to be positive. If theta 1 is 0, fantastic. My sine component will go to 0, my cosine component will become 1, but this equation is valid for all the angles theta 1. And this is your homogeneous transformation for 0h1. Everyone understood this? Now I want to write the homogeneous transformation for the second frame. And for that, I'm going to use the space over here because it's easier to visualize this way. Now let's start with something else. I want to find out the same homogeneous transformation for the frame 1 to 2. So step 1 is to find the rotation matrix 1 R2, 1 R, I need the space. So 1 R2 and 1 R2, believe it or not, we start with cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1. The next step is I need to multiply with the projection matrix, but this is the projection of, so here it's going to be x2, y2, z2, and here it's going to be x1, y1, z1. Now please recognize that my x1 is aligned with x0, y1 is aligned with y0, and z1 is aligned with z0. So how would this matrix look like, the projection matrix? I'm looking at the chat window. How would my projection matrix look like? This is gonna look like an identity matrix. Why would it look an identity matrix? Because check this out. Projection of x2 on x1 is 1, projection of x2 on y1 is 0, projection of x2 on z1 is 0, projection of y2 on y1 is 0, projection of y2 on y1 is 1, everything else 0, z2 on z1 is 1. Now I need to set up the homogeneous transformation. 1, 1, H2. And 1H2 would look like cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0, 1. And now I need to have the distances. Now, how do these distances look like? Once again, these distances are the distances between frame 2 and frame 1. So these are the distances between frame 1 and frame 2 expressed in x1, y1, and z1. Let's start with the easier one. In the z direction, I did not give you the distance. I need to give you the distance here. So let me call this A4 and let me give you this distance as A3. A3. So in the z direction, frame 1 and frame 2 are A3 distance apart, and A3 is positive. Why? Because if you go from frame 1 to frame 2, you are traveling in the positive z1 direction. This is super important. Why this z distance is positive? Because if you go from frame 1 to frame 2, you are traveling in the positive z1 direction. What about the x and y? So what happens here and what happens here? Please note, these distances should be projection on x1, this distance should be projection on y1, and this distance should be projection of z1. And it should be valid for all the values of theta. So what it means is, and I will write this down and hopefully you would agree with me, this will be A4 cosine theta 2 and this would be A4 sine theta 2. And that is how you have your second homogeneous transformation matrix.
Is that A4?
Yes, it's A4. And
Okay, thank you.
the reason that is A4 is because A3 is always going to stay constant. A3 is same. A3 is not going to change. But as theta 2 rotates, you are going to have a cosine component of A4 along x1 and sine component of A4 along y1. Are you with me so far? Yes. What? A3 be 0. A3 could be 0, but then that becomes a rest. So that becomes a rest, effective rest. And we will talk about a case where you have a spherical rest, which means you have 3 revolute joints mutually perpendicular to each other with the effective distance between the frames at 0.
I'm trouble seeing the physical joinage in the distances. A1, A2, A3, A4.
Okay, all right. Just for you, let me draw a 3-dimensional view. So this distance is A3.
So like A3 and A1 would be
And this distance, it depends upon the robot. And this distance is going to be A1. All right, now remember, I need to find H0, H2. 0, H2 is 0, H1 multiplied by 1, H2. Note, 0, H1 is here and 0, H2 is here. So you would substitute these values in the homogeneous transformation matrices, and guess what? That is where you have your homogeneous transformation matrices multiplied. Before I proceed further, I just want to make sure that everyone understood this setup. This is a simple problem, but I just want to make sure that we are on the same page. Any questions with the transformation? Could you go over the setup? Can you be more specific? What do you mean by setup? The how the problem is kinematic diagram, or? So you will always start with a kinematic diagram, identify regarding the matrices. So first you will have to find out, okay, I was going to go to the Matlab, but I think it might be helpful if I work out one more problem. So let me work out problem 2. And things will be super clear. This problem is, again, goes without saying, super duper important. This is classic robot. You will see this robot in lots and lots of applications. So what you have is, you have a revolute joint. This revolute joint is attached to another revolute joint. But please note, these two revolute joints are perpendicular to each other. Then you have a revolute joint. And then you have one more revolute joint. So you have another revolute joint. And this revolute joint is attached to the end effector. So this is your first revolute joint. This is your second revolute joint. And this is your third revolute joint. However, I want you to be super careful with this. The first revolute joint is perpendicular to the second revolute joint, but second revolute joint is parallel to the third revolute joint. So it's an RRR robot, but the revolute joints, first robot revolute joint is perpendicular to the second revolute joint, third revolute joint is parallel. Now, once again, I need to give you distances. So I'm gonna give you distances, but first let me set up the frame. This is going to be my Z0. This is going to be my Z1. This is going to be my Z2. And I will set up my Z3 like this. Then I will set up my XS. This is gonna be my X0. for the second for x1, it should be perpendicular to z1 and z0. So my x1 is going to be something like this. Now my x2 is going to be something like this. And my x3 is going to be something like this. Now we have to set up the right hand coordinate system. So x, z. Now do your finger twisting. This becomes y0, x, z. This becomes y1. This becomes y2. This becomes y3. Okay, any question about the setup? Now let's identify the distances between the frames. This distance is A1. This distance is A2. And this distance is A3. So I have A1s, A2s, and A3s. Everyone clear about the coordinate system and how the problem is set up? Because now I'm going to start with my rotation matrices. So this is my frame 0. This is my frame 1. This is my frame 2. This is my frame 3. So we have quite a few rotation matrices to set up. So I'm going to start over here. 0 R1 is going to look like cosine. Okay, let's identify the thetas. This is my theta 1. This is my theta 2. This is my theta 3. And please note, the reason I have theta 1, theta 2, theta 3 as shown because they have to be positive. So when you curl your fingers in the direction of thetas, your thumb should be aligned with z's. Okay, so let's set up the first coordinate, so rotation matrix. C theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Let's not forget the projection matrix. And the projection matrix, once again, I have to be super clear. This is x0, y0, z0. This is the old frame. New frame is x1, y1, z1. So let's look at the projection of x1 onto x0. That is 1, 0, 0. Projection of y1 onto x0. y1 onto x0. Is there any projection? y1 is perpendicular to x0. Can you see that? No projection. So 0. Projection of y1 onto y0. Is y1 aligned with y0? No. 0. But y1 is in the same direction as z1, z0. Are you with me so far? z1. Now, if you look at z1 is not in the direction of x1, it's in the direction of minus y0. So this is super important. So in this case, your projection matrix is slightly different than identity. And now we have to perform the matrix multiplication. And I'm going to do the matrix multiplication here. If you have problems doing matrix multiplication, review your linear algebra. So first row, first column, cosine theta 1. First row, second column, 0. First row, third column, sine theta 1. Second row, first column, sine theta 1. Second row, second column, 0. Second row, third column, minus cosine theta 1. Then third row, first column, 0. Third row, second column, third row, third column. This is your rotation matrix, the final rotation matrix. This final rotation matrix is going to be part of our 0, H1. This becomes cosine theta 1, 0, sine theta 1, sine theta 1, 0, minus cosine theta 1, 0, 1, 0, 0, 0, 0, and we have 1 over here. Now I need to find out the distances in x0, in y0, and in z0. So the distance along z0 is always going to be a1. So distance is going to be a1. What would be the distance x0 and y0? Since the frames are aligned, they are zeros. Now let's go for the second frame. So let's find out 1 R2. For 1 R2, same drill, cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1, multiplied by the projection matrix. Here it will be x2, y2, z2, x1, y1, z1. And let's look at the projection of x2 onto x1. They are in the same direction. So 1, projection of x2 onto y1, 0, projection of x2 onto z1, 0, projection of y2 on x1 is 0, projection of y2 onto y1 is 1, projection of y2 onto z1 is 0. And this is 0. So guess what? We got an identity matrix. And once we have an identity matrix, it's very easy to write. And I'm gonna quickly write the homogeneous transformation matrix. The multiplication by the identity matrix is the matrix itself. So which means when I perform this multiplication, I'm gonna have cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. And this will become my 3 by 3 matrix. Cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0, and 1. Now here, I'm gonna have x1, y1, z1. So let's go a step, the same step. Can you see that if theta 1 is changed, that does not affect the distance between frame 2 and frame 1. So only angle that is affecting the distance between frame 2 and frame 1 is theta 2. And if you look at if I change the value of theta 2, and I will write this expression and it will be clear, this becomes a cosine theta 2, a sine theta 2. And as you can see, their z's are already aligned, so you have a big zero. And that is the homogeneous transformation matrix for the joint 1 to 2. And once again, I want you to understand that this homogeneous transformation, especially the distances which are over here, should be valid for all the values of theta. Even theta is 0 degrees, theta is 30 degrees, theta is 50 degrees. These distances should be valid. Yes. Yes, thank you. This is A2. A2. Now, last but not the least. So I need to find out, and I'm going to use the space over here. Maybe I could write here in the bottom because it's easier to see the kinematic diagram and derive the equations. So now I have 2R3. Again, so 2R3 as frame number 2 is rotated with respect to frame number 3 by theta 3. So I would have cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1 multiplied by the projection matrix. And this projection matrix is between x3, y3, z3, x2, y2, z2. So quickly look at it. X3 is aligned with x2. Y3 is aligned with y2. Z3 is aligned with Z2. So which means when I start doing my homogeneous transformation matrix, the product of these two matrices is nothing but the same rotation matrix, because identity matrix does not change the matrix. So I can write 2H3 very quickly. I would say cosine theta 3 minus sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1. Then you have 0, 0, 0, 1. And then I need to add the distances here, which would be in x2, y2, and z2. So check this out. Z3 and Z2, they are at the same level. So I'm going to write a 0 here. But as theta 3 changes, this will become A3 cosine theta 3 and A3 sine theta 3. And that's it. So your overall homogeneous transformation matrix is, if you want to find out 0 to H3, you have 0 H1, which is this guy, multiplied by 1 H2, which is 1 H2, oh, 0 H, this guy, multiplied by 2 H3. So when you perform this multiplication, 1, 1, 2, 2 goes away, and you have 0 H3. And this is what is called as forward kinematics. And why this is called as a forward kinematics, it will be super duper clear in just a second. So I want you to understand, when I multiply all these matrices, I'm gonna have a big matrix wherein I'm gonna have the rotations. So let's look at the structure of the homogeneous transformation matrix. So consider a transformation 0H3. How did we get 0H3? We got 0H3 because we had 0H1 that showed the relationship between frame 1 and frame 0. We multiplied by a homogeneous transformation matrix that showed the relationship between frame 2 and frame 1. And finally, we have the last homogeneous transformation matrix that showed me the relationship between frame 2 and frame 3. No matter what happens, at the end, you are gonna get a 4 by 4 matrix, because first matrix is 4 by 4. You have second matrix that is 4 by 4, and you have the third matrix that is 4 by 4. And this 4 by 4 matrix again has a very simple and very important structure. So I will start with the bottommost row. The overall homogeneous transformation matrix would look like this. You are gonna have the orientation of 3 with respect to 0, and you are gonna have one quantity here, one quantity here, one quantity here. This is, and I have to be very careful here, this is distance. So this is x distance or x position. This is y position. And this is z position of the end effector with respect to initial frame. So this is the position of end effector with respect to 0 frame along, and this is super important thing, along x0, y0, and z0. And this kind of makes absolute sense because this is the homogeneous transformation matrix relating 3 to 0. So that tells me that this is the orientation of end effector with respect to the 0th frame, and the last column is the position of the end effector with respect to the 0th frame along x0, y0, and z0 axis. Everyone understood so far? Any questions? I'm looking at my chat window. Any questions? If there are no questions, I would go ahead and show you how to do this multiplication using Matlab. Now I'm going to switch the screen. So if you have Matlab in front of you, I would strongly recommend that you can open the Matlab. So share screen, and I'm gonna go for Matlab. So new script, you can do the live script. Let's stick to the old script, 0h1. So I'm gonna solve problem 2. Problem 2. Can you see my Matlab screen?
Yeah.
Yes.
Okay. All right. Problem 2. So we have to solve this system symbolically. So you have to start with SYMS, and there are 3 thetas. So I'm going to say theta 1, theta, or let me be a little lazy here. I would just say TH1, TH2, TH3. Also, I have the distances A1, A2, A3. So theta 1, theta 2, theta 3 are the angles, and A1, A2, and A3 are the distances. Now let's code H01 is the homogeneous transformation matrix cosine theta 1 minus sine theta 1, so TH1, so I see some question in the chat window. What is okay, are there any questions? Are there any questions? If there are no questions, I will just continue. 0 A2 multiplied by theta cosine theta 1 sine theta 1, so this is going to be 0 0 0 H1 0 semicolon sine TH1 0 minus cosine TH1 0 semicolon 0 1 0 A1 semicolon 0 0 0 1. So this is my first homogeneous transformation. My second homogeneous transformation is H12. That's going to be cosine theta 2 minus sine theta 2 0 A2 multiplied by cosine theta 2 comma sine theta 2 cosine theta 2 0 A2 multiplied by sine theta 2. Still we have a lot of entries. 0 0 1 0 0 0 0 1. H23 is equal to cosine theta 3 minus sine theta 3 sine theta 3 0 A3 multiplied by cosine theta 3 semicolon sine theta 3 cosine theta 3 0 A3 multiplied by sine theta 3 0 0 1 0 semicolon 0 0 0 1. Yeah, just a second. H0, just a second. H03 is equal to H01 multiplied by H12 multiplied by H23. Yeah, what is your question? You don't need the values for theta 1, theta 2, theta 3 because we are performing the calculations in the symbolic form. Okay. I'm going to look at the chat window for a second and see if there are any questions. Since there are no questions, I would start the problem. First, let's evaluate the first line. The symbolic variables are constructed. Then let's look at the first homogeneous transformation. And now I want you to take a moment with the homogeneous transformation that we derived and tell me if this matrix is similar to the homogeneous transformation or not. So please look at your notes and then look at the matrix that you have in front of you on Matlab. Then look at the second homogeneous transformation and see if this is the same homogeneous transformation that we have derived or not. So H12 is cosine theta 2 sine minus sine theta 2, A2 cosine theta 2, sine theta 2, cosine theta 2, A2 sine theta 2. Now let's look at the third one. Now let's look at the overall homogeneous.
Professor,
Yes.
both the signs in H01 should be positive.
H01. Oh, yes, you are absolutely right. Yeah, thank you. So someone found a mistake. Very good. Any other mistake? Anyone else? Any other mistake? If not, let's find the overall homogeneous transformation. And wow, that is a pretty long expression. But this expression gives us a lot of information. I want you to look at, first let's go step by step. This is the first 3 by 3 matrix. So I want you to look at, so let's go step by step. So this is the last column. Can you see you have this first expression that combines theta 1, theta 2, theta 1, theta 2, theta 3. That tells me the distance of the end effector from the base frame in the base frame x0 axis. So where is end effector with respect to base frame, and wherein that distance is expressed along x0. That's what this is all about. This is nothing but the distance between the end effector and the zeroth frame or the origin along y0. And this is the distance between the end effector and the origin of the zeroth frame along z0 direction. So this is the position along x0. This is the position along y0. This is the position along z0. And that is the meaning of forward kinematics. That means you now know the end effector position with respect to the base frame. Now let's look at the 3 by 3 matrix that we have over here. The first 3 by 3 matrix. That means, okay, so H03, 1 to 3, comma, 1 to 3. Okay, so this is, it's not working on the symbolic, but what I want, oh, okay, I see what happened. Yeah, it's not working on symbolic, but what I want to tell you is if you look at the first 3 by 3 elements of H03, if you look at the first 3 by 3 elements all the way from here to here, then you realize that is the orientation matrix. So now you have solved successfully the forward kinematics problem. So you can now tell me what is the orientation of the end effector with respect to theta 1, theta 2, theta 3, and what is the position of the end effector with respect to the base frame. Once again, we are going to spend some more time. There are 3 or 4 more problems that I'm going to solve with this technique. But this is basically the gist of forward kinematics. And I'm going to stop here. And actually, I would save this Matlab script. So problem 2. And I would upload this onto Canvas. And please look at the homogeneous transformation notes that I have added on Canvas. I have worked out this problem completely in that notes and some more problems for practice. So that's it for today. I'm gonna stop here and ask if you guys have any questions.